Okay. Very good evening to all. A very warm welcome to the 7th Professor Roddam Narasimha Endowment Lecture. Before we begin, a few words about this endowment lecture and Professor Roddam Narasimha. The endowment lecture was established by the former students of Professor Roddam Narasimha as a token of their love, affection, and respect to their guru and mentor. And those who have interacted with Professor Narasimha, he needs no introduction. But I see a large young audience here. It is good to see them. And Professor Narasimha was a multifaceted person. His contributions to various fields have been very original. He has been an outstanding teacher, a world-class researcher, a dynamic leader, and a builder of institutions. Born in Bengaluru in July 1933, Professor Narasimha was educated at the University College of Engineering in Bengaluru and at the Indian Institute of Science, Bangalore, and obtained his PhD from Caltech, USA. He joined the Department of Aerospace Engineering in IISc in 1962 and was associated with it till 1999. He founded the Center for Atmospheric Sciences, which is now called Center for Atmospheric and Oceanic Sciences, in 1982, and he headed it till 1989. He was the director of the National Aerospace Laboratories from 1984 to 93, and the director of the National Institute of Advanced Studies, which is on the other side of the campus, during 97 to 2004. He started the Engineering Mechanics Unit at the Jawaharlal Nehru Center for Advanced Scientific Research and continued to work and guide students till he breathed his last in December 2020. While his research interests were primarily in fluid dynamics and monsoon, they extended significantly to other areas such as education, philosophy, history, and history of Indian science, India's nuclear policy, and national security. He was the person behind the India's light combat aircraft. In fact, last lecture was on that here in this same auditorium. India light aircraft program, now it is called Tejas, and it is being injected into the Indian Air Force. He conceived of and pushed for the formation of the Ministry of Earth Sciences. And if you see the recent last 10 years, IMD has gained a lot of respect, especially weather prediction. And it is one of the major contributions by Professor Narasimha to conceive of improving this weather forecast in the country, and that helped improving this IMD's forecast. Many honors and recognitions came his way. I'm not going to read the list, which is very big, and they include Padma Vibhushan and Fellow of the Royal Society. These made no difference to his qualities. He remained humble and treated people with all walks of life with dignity. He was an extraordinary human being, winning a place in the hearts of many friends all over the world. In fact, the tip of the iceberg is a line in Sanjay Baru's book titled, I think the book is not easily available in India, but it was written, The Accidental Prime Minister, the Making and Unmaking of Manmohan Singh. That is a book published in 2004, where the author says that Roddam would have been a far superior national security advisor. It was referring to some person who occupied that post. He said Roddam would have been much for this thing. This shows how much respect Professor Narasimha commanded among Indian bureaucrats. Today, we have a very distinguished speaker, Professor Katepalli R. Srinivasan, and we all fondly call him Srini. And inarguably, he is the most distinguished PhD student of Professor Roddam Narasimha. He has traveled all the way from New York to Bangalore at his own cost to deliver this lecture, showing how much affection and respect he has for Professor Roddam Narasimha. Now, may I request Professor Rangarajan, Director IISc, to preside over the function, introduce the speaker, and conduct the proceedings. Thank you.
So it's my pleasure to welcome all of you to the Professor Roddam Narasimha Endowment Lecture. And let me briefly introduce the speaker. Professor Srinivasan is a renowned expert in fluid dynamics, turbulence, and applied physics. At NYU, he holds the distinguished titles of University Professor and Eugene Kleiner Professor of Innovation, professorships in physics, mathematics, and mechanical engineering. He served as the Dean of NYU's Standen School of Engineering and led the International Center for Theoretical Physics in Trieste. A member of some 10 renowned academies, Srinivasan has received numerical international honors, including the UNESCO Medal for Promoting Global Scientific Collaboration. His groundbreaking research explores universal aspects of turbulence, ranging from quantum vortices to large-scale convection in stars, and he has recently ventured into hybrid quantum algorithms for simulating fluid flows. He is a passionate advocate for scientific cooperation and human rights and led the American Physical Society's Committee on the International Freedom of Scientists. He is a former student of Professor Roddam Narasimha. With these few words, and let me also add, it's not that he's still going strong. I recently came to know that he has been awarded Trailblazer Grant by NSF, one of the 5 to be awarded in the whole of US. So that shows his commitment to research and his ongoing, research activity has been well recognized even now. Professor Srinivasan.
First of all, I should thank Professor Bhatt for making the remarks about Professor Narasimha, which means I don't have to say some of the same things. I appreciate the work, Professor Bhatt, that you and the other members of the committee have put in over the years in finding suitable speakers and in making sure that the program works. I also appreciate Professor Vinay Chandran, you chair the committee now, I know, and all the other members. The chairman of the aerospace department has actually contributed a lot to making sure that this thing works. I feel confident because of the involvement of a number of people here that this lecture series will continue for many more years. It's one thing to end of a lecture, but it is quite another to make sure that it works well, and therefore very grateful to all of you. Director Rangarajan, thank you very much for your kind words about me, and also for chairing this, and you chaired this lecture as well, I know, all of them. And it shows your commitment to our cause. And I appreciate that a lot. I also appreciate the fact that you've been very kind to me personally for all the years I've known you. I especially appreciate the fact that Dr. Nilima Narasimha and Professor Maitreyi Narasimha have generally always come to these talks. Today, Maitreyi is here. I see her sitting there. And their involvement to some degree adds a level of depth to the whole thing, which I appreciate. And likewise, I am very grateful to all of you for being here Friday afternoon at 4 o'clock. That is to be commended. And some of you have traveled quite a long distance, I know that. Not as long as I have, but still. And I should point out that even though Anurag Kumar, the former director of IISc, is not here, he was responsible to some degree for setting up this lectureship. When I approached him, he very immediately responded and presented it to the council, and the council enthusiastically approved it. So he and the people, a group of people who worked with him, including Rangarajan at the time, were very instrumental in getting the lecture established. So I should thank them all. By the way, it just goes to show how many people it takes in order for an event like this to happen. Just amazing. So I feel that I owe all of you a great deal of gratitude. Now, it's almost 5 years since Professor Narasimha passed on, and much has been written about him, and much has been said about him. And I myself have written a number of articles in Bhavana, Current Science, etc. They were all written very close to his passing away. And so they were very personal. And I also wrote various professional obituaries in Physics Today and the memoirs of the US National Academy of Engineering and of the Fellows of the Royal Society. This one here is a part of a volume which Maitri has, and this one will be a part of the volume, and I will send that to her. But you can actually access it very easily on the web anyhow. And then I also say that I spoke on Aran and his work at the Indian National Academy of Engineering, Bangalore, and DRDO, Hyderabad. And then I spoke about his work, sort of. But today, I am particularly honored to give this lecture, but I will speak about things that he didn't work on, and as far as I know, never really thought about. But I know that if he had lived on for a few more years, he would certainly have looked into it as well. So, but before I say too much about the subject, I have to manage your expectations on this. So basically, figuratively, let's say, suppose this is the desired train that I wanted Ms. Navier from France and Stokes from England to take and come to City Central Station in Bangalore at 400 or 500 kilometers an hour. That's the kind of train I would like them to have taken. But you should know that it is, I think it is like that at the moment. So that's the management of expectations. I won't be able to get further than that today. And I know that the Institute has an activity, an important activity. It says pioneering quantum innovations. So if I say that the progress in this subject, the one that I'm going to talk about, is compared by these two trains, they should not feel offended. I mean, it doesn't mean that they are not doing a great job or things are not going greatly in their center or in their institute or in their activity, let's say. But you will see what I mean as we go along. Since I have a feeling that quantum computations are not particularly well known to everybody here, I will start slow But presumably, I will get to a point where even for the experts, there is something that you might not know about. My plan is to discuss QCFD, as I called it. This is a picture of one of the computers. FD stands for Fluid Dynamics, which was Professor Narasimha's central activity. And CFD, which is a big business now, is computational fluid dynamics. By the way, for that activity as well, Professor Narasimha was very supportive in Bangalore. So you just add Q, which is an acronym that we sort of invented a few years ago during COVID period, which is when I began to look at this, this topic. Let me now say a little bit about CFD first, in contrast, to provide a contrast for QCFD. CFD is now a big activity, as I said. You can look it up and see, as an industry, how many billions of dollars are being spent on it. That's a few $billion. And it's actually growing at a reasonable rate. But that may be interesting to you if you want to invest in CFD companies or something like that. But the best you can do as a challenge problem is that you can take turbulence on a grid of 32,768 cube periodic box. If you stare at the authors, you will actually see my name as well. That's the best you can do today. And if you look at what Steve Arsog was able to do in 1972, approximately 50 years ago, he was able to do calculations only on 32 cube grid. So it's actually grown a billion-fold in size. That means we obviously know a lot of stuff about the subject than we did before. So that's really how far the subject has gone. And it's been possible to do that because of computers like this, which is the exascale machine frontier, which can do 10 to the power 18 64-bit operations per second. You just have to think a second as to what 10 to the power 18 means, a billion times a billion, all of that in 1 second, and the 64 bits of words. Now, as far as I can see, the technology of digital computing, both hardware and software, has advanced in the last 6 decades or so, unlike any other scientific tool. I actually sat down to look at, let's say, particle accelerators, which are really have advanced as well, and also other scientific instruments people use. And it's very hard to know any other device that has grown that fast and that much in those years. Now, why QCFD then? Why do I really bother about quantum computational fluid dynamics? One of them is that I plot here the speed of the computers, this is in gigaflops, as a function of time, and just concentrate on this. It's growing exponentially, but then again, another exponential perhaps, which is about half as fast as this initial period. It's possible that it will pick up some time one of these days and go back onto this, but it is unlikely. I say unlikely because if you look at, let's say, the frontier, how much space does it take? It takes that much space, which is about half the area that you have dedicated to undergraduates here in the institute. And it takes 25 kilowatts of power, which is roughly comparable to what Tungabhadra Dam generates. It's a huge amount of power, huge space, and it's very hard to see how it will keep going. And furthermore, technologically, the miniaturization of the ingredients of making these machines, you cannot really go further beyond what physics dictates. And it looks like we may have been reaching the limit. So if I'm interested in solving problems of interest to big problems, let's say this is the size of the problem here. As an example, the sun or cyclone or something like that, let's say, and this is time. Even if you assume that actually the thing goes on, keeps going forever, which I suspect will not happen, but okay, maybe I will be wrong. So it will keep going like that. It will take another 100 or 150 years before you can solve a problem like that. And it will certainly be after my time. So the paradigm that one has in front of us, which I will describe, could be this quantum paradigm. So maybe it's now really far below the capacity of regular digital computers, but perhaps it will take off. Okay, we will see whether it will or not, at least in how I see it. So if you look at an IBM blurb, IBM is a commercial company, but nevertheless, it's a respectable company. By taking advantage of quantum physics, large-scale quantum computers would be able to tackle certain complex problems many times faster than modern classical machines. With a quantum computer, some problems that might take classical computers thousands of years to solve might be solved in a matter of minutes or hours. That's the quantum advantage. That is, you can solve much bigger problems and much faster. If they are not much bigger and can't be solved faster, what's the fun? I mean, we might as well stay with regular digital computers. Now, how can one resist the temptation? Okay, so there is a need in some sense. I would like to see this to take off somehow. And in fact, there is a claim that it will do far better. So why not give that a try? So what's the potential of the quantum computer? Many of you know all this, but I will say this anyway. So digital computers work on bits or binary digits, and they're 0 and 1. Digital computers just manipulate these things. That is all it is. And they use clever rules and control gates and logical memory and all that. And when I was at Johns Hopkins, I took a course on programming the machines themselves, that is, by manipulating bits and so on. It was a pretty boring course because there was not much physics in it. But okay, some people like physics and some people don't. But now, as a contrast, quantum computers work with quantum bits, which are known as qubits. Now, they represent some physical thing. For example, the spin of an electron, let's say. If it is spinning up, let's say, you write it in this notation, which is the Ket notation, which is very standard in quantum mechanics. Or down, if it is spinning with an arrow, you can imagine pointing downwards, it could be written like that. You should not be intimidated by this notation because it's very standard. And instead of that, you can write them as two standard states, which is Ket 0 here and Ket 1, this representing upward spin and this representing downward spin. So this is two vectors in a so-called block sphere. So that is what the sphere is, and I have two of them There's 0, ket 0, ket 1 here, and any other things. Now, the thing about these quantum or qubits, as they're called, is that if you leave the bits alone, strictly 0 and 1, they will be there. But these qubits, they can be in a superposition state. That is, if you sort of operate on them somehow, there could be a superposition of the ket 0 state and ket 1 state with certain coefficients sitting in front, which have to satisfy the notion that alpha squared plus beta squared equals 1. And how you get the values of alpha and beta depend upon what kind of initial state you load these vectors into your machine and what kind of unitary operations have been performed on it and so on. But let's not worry about that part. Now, but the important part of that is the so-called wave function collapse. That is, these vectors might be doing anything on this Bloch sphere when they are operated upon by something. But as soon as you look at them, then they will collapse onto either this or that with a certain probability, which is alpha and beta. So this is alpha squared plus beta squared equals 1. So somehow this is the mystery of quantum mechanics in some sense. That is, the observer is at least one interpretation of it. The observer is somehow a part of the whole ambience, let's say. So this is an amazing thing that somehow you have to be, when you actually measure it, these qubits tell you give you some information, but it's really not all that there is. And your job is to figure out, in spite of this property, exactly what you want from operating on these qubits. Now, why is this idea very powerful? With one qubit, let's say, or 2, you have 2 basis vectors. Let's say if you have n qubits, then you will have these Bloch spheres which are independent. Now, tensorial products somehow you have to think about. Many Bloch spheres all connected in some way. Or mathematically, you might say, just takes a Hilbert space of size 2 to the power n. That is, one can store and manipulate all possible binary strings in parallel using this property. And this is the exponential advantage that one has with respect to classical qubits. For example, I showed you this big calculation with n equals 32,768 cubed. This is now what, 1 trillion classical grid points or something like that. But if you just use that idea, you only need logarithm to 2 base 2 of this n, which only is 45 qubits. So in principle, 45 qubits will be enough to store all these trillions of data points you have. And of course, there are there are computers today which have, say, 1,000 bits or something like that. So you might ask, why am I not just loading them onto those, loading this data onto those computers and work my way through them? As we will see, there are big caveats about it. And the other theoretical advantage is that quantum operations are unitary. That you just run the Schrodinger equation, which is basically you just operate with the unitaries. And they simultaneously act on all components of the superposition. So somehow there is a built-in parallelism involved in quantum computers that you don't have in classical machines. And in fact, it turns out you can do a number of operations much faster using quantum computers. For example, you can do the quantum Fourier transform, which is the quantum analog of the fast Fourier transform that one has, or use this HHL algorithm, so-called, for solving linear systems. If you have AX plus B inverting the whole system, that is what it is all about. It can be done on the scale of logarithm of n, rather than n log n, which is the big thing in fast Fourier transform, for instance, or matrix inversions. Now, this is exponential speedup. I mean, if n is very large, you can imagine the cost differential between the two. So that's a very big advantage in being able to do that. This is another property, which is the so-called entanglement. That is, if you have two quantum objects that are entangled somehow, which is more than just a correlation, then you can describe them only together. You cannot describe each of them independently. That is, if somehow two quantum particles were entangled to start with, and they were both prepared in New York City or something like that, and I was able to transport it to Bangalore without any interaction with external things, then they would be entangled. That is, the two of them have to be described together somehow. So they will remain like that, and this is an important property which, of course, you don't have. You should recall here, just for the sake of our remembering the great man, Einstein had many objections to quantum mechanics, as you know. One of them is this spooky action at a distance. So if two electrons, let's say, somehow remain entangled between two states, you can know about one if you know about the other. And Einstein thought it was information traveling faster than the speed of light. And of course, that is not the case. And this all got sorted out recently. And a few years ago, a Nobel Prize was given for this kind of work. And if you recall, that wave function collapse occurs whenever you make a measurement. This means that the measurement of one quantum particle changes the entire universe, albeit microscopically. And this, of course, also Einstein didn't like. And so, I mean, many philosophers and cultural gurus take advantage of these things and make big things out of them. These may be difficult to understand, but quantum mechanics is difficult in some sense. And you know what Feynman said, just shut up and calculate. Maybe that's a good recipe for it. Now, given all these peculiarities, if you write a quantum algorithm, you have to be able to extract information you want in spite of all these. Somehow there are advantages sometimes, and sometimes they're a pain in the neck. Now, these are all some theoretical advantages, but let's see what the real quantum devices suffer from. That's very important to know. And one of them is the measurement problem. Measurements collapse data on the basis vector. Thus, one can extract only limited information about quantum objects. It's like these qubits are very shy. As soon as you look at them, they will forget about what they're doing and get onto a certain state, where you expect them to find. And decoherence. An isolated qubit relaxes to a mixed state. That is, its tip does not go around in a Bloch sphere, but actually shrinks. And it loses the original information stored on it. And data can be corrupted also because this vector will not stay fixed, but it jitters around, and you have a problem of loss of information that way. And I already alluded to noise and error gates. There is a faulty gate action can lead to flipping of qubits. And the error rates today are not very small. It's 10 to the power minus 3, let's say, in some cases. That is, if you do 10 to the power 3 operations, you have error of order unity. And that's no use, because you're used to doing billions of operations. And then some superconducting devices have pushed it about 1,000-fold smaller. But then what is 10 to the power minus 6 in this business? You really need to get it down to many, many, many orders of magnitude. So presently, this necessitates extremely compact circuit designs with low depth calculations you can make in spite of all that. And then the other important thing is that quantum information on currently available devices is very short-lived, of the order of 100 microseconds. So let's say you have these machines in IBM, and you want to make these calculations. You better finish your calculations before the bits, these qubits lose their memory, and you are 100 microseconds. So it means you can do today only very small calculations in spite of all the promises one has. And furthermore, I already said some machines have 1,000 qubits, 1,115 last time I looked. But that's not enough, because these qubits are very sensitive, and they might lose their memory and things like that. So what you have to do is to make sure that their integrity is preserved by entangling them with a number of other qubits nearby, so their integrity is preserved. So essentially, you need much larger number of qubits in order for things to work. And the number of useful qubits are called logical qubits. So what you need is not 45 qubits, but 45 logical qubits. And how many logical qubits can you have, or how many qubits are required to make sure you have one logical qubit? That depends on the design and what's going on, what architecture one uses, whether it's superconducting things and so on. It could be 20 to 1,000. If it is 1,000, for instance, if you want 1,000 qubits, you better have 1,000 times number of qubits. Well, that is not it there. So these are all the challenges one faces. I want to tell you a little bit about where it has already worked and the reality check on that. A good example is data encryption. As you know very well, these data encryption codes, which are known as RSA, named after the last names of the inventors of this encryption. And it depends on the inability or the difficulty of factoring very large numbers into primes, is the prime factorization problem. In the digital computer, what you can do, or what you may have to do, is equivalent to sort of taking a very large number. Large number means something like that. It's not just a large number we are used to. This is much bigger than any number of particles, and including the smallest particles in the universe. That doesn't matter for computer scientists. So if you want to factor a number like that on a digital computer, the expectation is it might take thousands of years on a fastest machine. This is where the IBM thing, 1,000 years, thousands of years, comes from. Now, classical factorization, as I said, basically dividing a number by every possible number and finding out where you get the primes. It's better than that, but it is something like that. And the complexity is about n to the power a, where a is a number of order unity, and n is the number of digits. Now, this, therefore, the information you send, the encrypted data, is very safe because the other party doesn't know how to factor these things fast enough. But the thing that got everybody excited was the Shor quantum algorithm, which said that you can actually factor the numbers like that, not on the order n, but log n cube, let's say. So you can imagine what difference it would make for such large numbers. This is the exponential speed up, and the impossible could now be done relatively fast. That is, information is supposed to be no longer safe. Of course, we will see whether it can be done. This is a possibility, theoretical possibility, and the algorithm is all there. But it's a question of implementing them on a real computer. And there are also search problems. Instead of order n steps in searching through a big database, Grover's algorithm goes to square root n, which is not as good as the other one, but still it's very good for very large numbers. Now, such potential speedups have driven the research and investment in quantum computing, and it's a motivator for developing quantum algorithms capable of actually running on a real computer. And if you look at how much money has been invested on quantum computing, again, if you are a person who is investing in stock market, you will see it's been growing up in the last few years exponentially, and it will go like that for some more time for sure. But this is great. But how big a number has actually been factorized on a real computer? This would be interesting to all of us. So the largest number that's been factorized like that is 21, not 2 to the power 8192 cube. 21, 7 times 3. And this paper appeared in Nature. So the only paper you can write in Nature with the number, with things like that. 21 is 7 times 3. So that's the difference between what's possible and this with the prior knowledge. This is not like they say it's okay, we'll go start from scratch. And of course, there have been other numbers that have been factorized or factored, but they are really not following quantum algorithms. They use hybrid classical quantum methods, which is very important, and also heavy lifting there is done by classical computers. So what about physics? All of this is great, right? I mean, computer scientists always do things like this, which are very important, but somehow the physics content is not there. So let's see what physics is about. So the great man, Feynman, you can read it in his paper. Nature is in classical, damn it. And if you want to make a simulation of nature, you would better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. Actually, in the printed version of this remark, damn it and by golly is not there. But on the web, you go anywhere, everybody says, damn it and by golly. This is really consistent with Feynman's character in some sense. So people leave it alone, I guess. So what was he actually talking about? Let's see if I can explain that. So this line divides the universe into 2 parts, and the 2 parts are classical and quantum. So that's classical and that's quantum. This is a mathematician's way of dividing things. And then I draw a horizontal line which divides below, above, let's say, classical computing with bits and quantum computing with qubits. So you can sort of make a diagram like this. This is classical problems using classical computers, which is CFD, for instance, which is thriving very well, as we know. And then here is quantum problems using quantum computers. This is probably what Feynman had in mind. That is, for example, you want to calculate the configuration of a big molecule that gives minimum energy or something like that. And what people still do, is that's a quantum problem, quantum chemistry, let's say, using classical computers. So you sort of put the whole quantum mechanics in the framework of bits and so on, which is not the natural language for it. And then you would try it, and it takes forever to do that, not very surprisingly. So I suppose the idea would be for people who work on quantum problems, who the problem is quantum, then they have to transition from here to here. That would be a great success of quantum computers. Now, we have classical problems which are immense in applications, especially. Fluid dynamics belongs to that. Now, classical computers do very well, but I already said why we must think about quantum computers. Now, we are looking at, can we really gain something by going classical problems with quantum computers? That would be my goal in what I want to say for the rest of the time. Now, one nice thing, one important thing that occurs to me is that classical computers lets you almost ignore physics unless you are designing hardware. I mean, as I said, I took a course where there was no physics, whatever. You could just do this kind of mindlessly if you know some rules. Whereas in quantum computing, you better know some physics, quantum physics, before you really produce an algorithm. So that, I think, is very interesting. It really brings physics and computer science together. And it's possible that being able to compute quantum phenomena will also show some limitations of some ideas of quantum mechanics as well. So the possibilities and barriers and how to overcome the latter with respect to fluid problem that I started telling you. So let's see what our goals are. QCFD, barriers, and how much can be done to overcome. So I have here a jet. Jet could be replaced by any other fluid flow that you are interested in. And you want to somehow compute it. And you want to go directly to your quantum computer, quantum algorithms, like what I have said. But at the moment, it's just not possible. It's just not possible for reasons you will see. So why is it not possible? Because there are barriers. There are barriers which relate to state preparation, nonlinearity and dissipation, and noise and decoherence. About this I have said already a little bit. Quantum mechanics, as you know, is linear and unitary, and real flows are nonlinear. Turbulence is a notoriously nonlinear problem, and it's highly dissipative. So you can't do it directly because you will somehow have to deal with all that. And as a practical matter, instead of going directly here, it turns out that if you use these quantum algorithms where it's possible, along with classical supercomputers and with machine learning, which is really important, as you will see, for practical considerations, we might make some progress. So that's my theme. Now, what about quantum state preparation? What's the big deal? The big deal is the data we have in the classical world is in terms of bits. And you somehow have to transform this information in bits to qubits. And that is non-trivial. I mean, you can do that. It's very easy to do it if you have just a few bits or something like that. Even I can do that. But the problem is, if you have a lot of data, you somehow have to load it like that in qubits. And this is the reason why quantum computers can slow down. I mean, even if you had a machine that can actually work very well, fast, but the act of loading takes so much time that unless you really emphasize the end-to-end advantage of quantum machines, you are not really giving a good picture. If some small piece of the software can work much faster, that doesn't mean it by itself. So it follows that quantum computing is most promising when the data are either inherently quantum or somehow you have algorithms that can look at the structure in the data and don't need to do it all directly. One day, however, I am pretty optimistic that high-level programming will make this data loading less complicated. For example, how many of us think about the complexity of how bits work on a digital computer now? We don't. And I think with time, this will certainly change. Now, what about nonlinearity? As I said already, quantum mechanics is linear, and flow problems are almost always linear. Any numerical scheme for solving nonlinear flow equations requires a quantity like u squared, let us say. You think this is very trivial. It's very trivial on a digital computer, where you can actually make a copy of one thing and just say multiply, and it will multiply. But in quantum world, it is not trivial at all. First of all, multiplication is very hard. You can do only certain limited things. And there is this thing sitting in the middle of the room, which is called the no cloning theorem. No cloning theorem means within the quantum world, you cannot make a copy of what you already have. This is just not possible. So that means this is a fundamental thing. It is not a limitation of a machine, which means that if you have to get u squared or u times du dx, let us say, it's not possible to do it in a straightforward way. Of course, what you can do is when you load it into the computer, you load u squared, u cubed, whatever you want. But then loading is such a time-consuming affair that you are lost. You're totally lost on your advantage if you gain any at all. And dissipation. Now, you know that everything you do in quantum mechanics is dealing with the Hamiltonians, and you have the issue of hermeticity of the quantum propagator. That means you have, which is known to many applied mathematicians as self-adjoint property. And self-adjoint property has many advantages, like real eigenvalues and things like that. But if you don't have any dissipation, that's perfectly fine. But once you have it, you no longer have Hermitian properties. And so you'll have to use a Hermitian conjugate, which is constructed something like that. So instead of AX, you'll have A transpose times A times X equals B. And you can solve that. That is perfectly Hermitian. But you are actually solving a kind of different problem. And this is known, very well known in hydrodynamics, especially people who deal with linear stability and things like that. Now, so dissipation remains a problem. How are you going to get around it? But we somehow have been able to show, you will see, for something like burgers, which is a simple nonlinearity compared to Navier-Stokes, but it is dissipative. You can combine 4 unitaries into to make up a non-unitary operator or a non-Hermitian quantum system. But you can do this only for a period of time. That is, it doesn't go on for very long. So you will have to have some hybrid quantum classical algorithm to make it work. So let me say one more thing to your disgust if you don't like it. But I have to say this, which is very important, which is about artificial intelligence, machine learning, and neural nets, and deep learning, and quantum machine learning. Okay, now I added QML. I mean, it's not me who added it. It's been there already for some time. Now, some of us do not like AI, but I think it has many virtues, and we should sort of take them in our stride and work with them. So classical machine learning takes many forms, which is you have an input layer, and then you have an output layer. You feed the data into the input layer using different weights and so on, and let the output layer produce whatever you want using different weights and so on. And of course, that's a very trivial way to do it. And it used to be like that when I was a youngster. When I went to Yale, artificial intelligence was being practiced. It was like that. It was pretty trivial, and it was never really that important for that reason. But now you add extra layers in between. Like here, you have the input layer, you have the output layer, and you have in between a number of other layers which never see the input layer or the output layer. And these are the important things. And this is the structure of the so-called deep networks, depending on how many of them there are. And I don't know, maybe there are in Chat GPT, if you use it, they probably have 100 of these layers in their machines. And all of this is possible because you have very fast computation. The quality of them depends upon how well they train on the basis of these different weights and these nonlinear activation functions. And in fact, it turns out they are so powerful these days that you wonder why you are solving differential equations. It's really come to that somehow at some level. Now, how does quantum part work in there, which is really my reason for bringing this up bringing that up at all. And one of them is apply quantum computing to speed up some machine learning tasks. You have these machine learning tasks, and some of these intermediate ones can, let's say, be done faster by quantum algorithms. Well, why not use that? And that means you replace deep learning layers, which are here, by some quantum circuits which use gates and things like that. And you can do that kind of stuff. And maybe quantum tunneling will become useful one day for this kind of stuff. I think it will be very powerful anyhow in the end. And the other way is use classical machine learning to optimize quantum algorithms, which you can do and which you have to do. Otherwise, you can't really solve these problems of this sort of interest to us. OK, so now there are ad hoc methods, which I will not talk. So far, what I've said is the excitement about quantum computing, why QCFD in particular and its limitations, and what may be a possible program, looking at it for a 10-year horizon. At least that is my limit for now. So I will present our work on this, not in great detail, by just actually showing you some papers we wrote. And then Bharadwaj is my former student who is now a postdoc. He is one of the outstanding students I've had. And we wrote a few pedagogical papers. The one at the top and the one at the bottom are written with him. And this one we wrote in honor of Professor Narasimha, again saying that he really would have been able to appreciate all this had he been alive a little bit longer. And then we wrote a few papers which are pedagogical introduction to all the quantum algorithms possible for simulation of fluids. And this one in particular was talking about how instead of using Navier-Stokes type equations, you use a functional Liouville equation, which is linear for the probability density of the field configuration. And actually, it's a very promising thing. In classical fluid dynamics, it's not practiced as much because simply there are too many particles you need to have in order to get any data. But if it's a linear problem and somehow quantum machines are really very fast, as we think they are, then maybe that will work as well. Okay, and that is just pedagogical. If you're interested, you should read one of those. Specific results are that one of them is this so-called linear embedding, quantum linear something algorithms, system algorithms. So what is the standard way to do that? You probably know the Carleman way of doing this. This is to say, take the nonlinear system and sort of expand it into an infinite dimensional linear problem that will be equivalent. And now, of course, you have elevated the dimensionality of the system, but it is linear. The thing is, of course, you can't do anything with infinite dimensional ones, so you have to truncate it. And once you truncate it, you don't know exactly where you truncate, what errors it has, and this becomes an important part of the whole thing. So what we did here was to improve upon what exists already and also provide new complexity guarantees that you should know that if you truncate at a certain level, what kind of errors you will have, without which the whole thing becomes meaningless. And the error growth and how strong the nonlinearity can be when you truncate this infinite dimensional matrices. In other words, this puts a limit on the Reynolds number up to which you can use these things. And I will tell you very briefly about that too. Now, I already mentioned this. If you have non-unitary that you want to somehow operate on, for certain conditions, you can express it as linear combination of 4 unitaries. And then you can use a hybrid algorithm to efficiently perform things like matrix inversion. And you can work on that a little bit. I will say a little bit about that. So there are problems. Problems are numerous, but you can use it maybe for low-dimensional systems. Then you have variational quantum algorithms. That is, somehow you don't do everything on the quantum machine, but you input a certain approximation to the solution and then use the quantum part to hasten the refinement of this approximation, and then measure at the end one number, such as the efficiency or optimization parameter, something like that, and you feed it back into the quantum machine, and it's the kind of thing you can do. And this runs into very easily barren plateau problems. That is to say, it will plateau out, but it plateaus out really too soon and probably to the wrong one sometimes. And there are no complexity guarantees on this. That is to say, there's nothing that tells you when it plateaus out, it's plateauing out to the right one. And this is the homotopia analysis, which I think will be interesting. Now, suppose I have 2 functions, one which is here and one which is here, the black and the magenta. And now call this F and call this G. And now you create a homotopy from this, which is 1 minus Q times F plus Q times G. And Q is an embedding parameter between 0 and 1. Now, if you say Q equals 1, this disappears, and you have simply G. And if you put Q equal to 0, well, that disappears, and you have this entirely. So either of these two curves. But by working on Q, you can actually transition from this to this in some fashion. So it's sometimes possible. And so what you have to do is to write it down like this, using as an approximation to the solution somehow. For example, if you have a nonlinear problem like the burgers, which is nonlinear term and the diffusive term, the approximation could be the solution of the diffusion part. So let's say you start from there, and somehow you expand that solution in terms of Q. As Q goes from here to here, it's an expansion parameter involved there. And then you get a very high dimensional linear system. And you can use all the tricks you know about inverting matrices. It depends on its sparseness and all kinds of things. And as I said, we already have improved upon the existing ones already known. And you can actually solve some problems using this. With respect to time, just schematically, let's say that is your u as a function of time. And this is your approximation, the diffusion approximation, or something like that. And you have this series which add to this approximation. And it actually, you can make it work up to a certain time, as I have shown here. And beyond this time, the two things diverge from each other, and you cannot have any real solution to the problem. So we have an idea of the time involved and all this kind of stuff. For example, here is the solution of the burgers, and you have the shop here, and this depends upon the number of terms you have in your expansion, and it seems to work pretty well. And in fact, you can calculate the root mean square error, that is the difference between the real solution, which you can calculate using digital computing, for instance. And as a function of the number of terms, it sort of comes down as you expect, and that is as you want, and that is really very nice. And here is the time evolution of the same problem. You start out here, and then you get into steeper and steeper ones with time. So it can actually be made to work, at least on some problems like that. And then the other important and interesting thing is the so-called lattice-Boltzmann methods. You will see why it is important. And my graduate student, Vail Itani, who is now a professor, he did the work. And just recall that lattice-Boltzmann method is, instead of dealing with molecules in the flow or fluid, even fluid particles, it has a mesoscopic particle in mind, and there are a number of mesoscopic particles that actually they stream around, and then they come to, for example, they live only on lattices. They don't go anywhere as fluid particles might. So they go along these directions, and the motion consists of a streaming part where they are not interacting with neighboring particles, and then there is the collision part, where they come together. And the nice thing about this is the streaming part is linear, so there is no nonlinearity to it at all, which is a very nice surprise. And you cannot separate in the Navier-Stokes, for instance, the streaming and the collision part. And the collision part, you can actually use something like the BGK approximation, where you have a relaxation time of between what you have at the ith iteration and the equilibrium value that you can get. So now this actually becomes easier in some way. First of all, lattice-Boltzmann methods have been successfully used in many cases, but you have a linear part now, and half the load is somehow taken off, and you have the nonlinear part for the collision. So you can actually do this, and you should not take me very seriously on this, this particular one. And this is from the thesis of Weil Itani. So I always pushed him to solve a problem, not just go theoretically saying, well, this is possible, and that's not possible. And this is the cavity flow. So you have a cavity like this and the flow going up like that. And then over time, this is the steady state solution, which you can calculate using Navier-Stokes equations. This is for one Reynolds number, and this is for another. Both of them of the order 10. I mean, that's, even then you have problems, as I will explain. And so he used lattice Boltzmann methods, and he had great difficulty with collision terms. And so he started using machine learning in order to augment his calculation methods. And what did he find? He found that if he uses all possible velocities, you'll get something which looks like crap. I mean, it doesn't look anything resembling the real problem. However, if he cut off very small velocities, because the errors are very large, and when the velocities are small, the errors sort of overwhelm the actual numbers. If you cut them off, you will get a solution that actually resembles what you have in the real Navier-Stokes case. So that's, and there's some details here. Boundary conditions are applied. Classically, that means you have to do a quantum calculation, come out of the quantum system, and then reload the problem. And this is partly why you need something like a machine learning algorithm to help you with it. Otherwise, it takes too long. So basically, I can now conclude my talk with a perspective. I do want to say that I greatly appreciate Professor Narasimha's memory, and also my association with the Indian Institute of Science and Bangalore institutions in general. They've been very kind to me in many different ways. And I have given many lectures in this hall. In the last few years, I always said to myself, it's probably going to be my last one. So anyhow, who knows? That may be so, may not be so. With that, let me present something here, presented with great trepidation. I think you should really take me seriously on it. And with restriction to physical problems, that is to say, I'm not really much involved in cryptography and data encryption and all, which I think is a very important problem which a lot of people are working on. And my time horizon, as I said already, is 10 years. It would be nice if I could foresee what happens beyond that. OK, now quantum computing market is growing exponentially. And so the interest in it is growing exponentially. And some of it is no doubt hype, and it will abate. I mean, there is no doubt about that at all. But these developments will be important for science at large, not only for quantum problems. I mean, one day you may discard DFT, for instance, and actually do quantum calculations without this thing. I am optimistic about improvements in data loading algorithm, which is really a big hurdle at the moment. And if you want to do it by hand, it is very hard. Breakthroughs in hardware development is clear. It's going on many places, probably even here, which I do not know a great deal about, including building of quantum computers with large number of logical qubits. This will happen. And it is more or less keeping with expectations, although expectations are never fulfilled 100%. And the error rates will reduce, and convergence guarantees will come, all of that. And quantum computers will achieve true utility at some point. It's now only a toy problem device at the moment. On the third quadrant of my representation, that is quantum computers for quantum problems, it's very natural to expect some real important advances, such as in quantum chemistry. But I do not know at the moment any exponential speedups, even there. So it will probably happen, maybe in a matter of time. But in the fourth quadrant, which is the fluids type problem, classical problems solved on quantum machines, quantum computing is unlikely to replace classical computing. However optimistically I started, I cannot exactly see in that time horizon how this might happen. However, there will be and already are many instances of quantum-assisted classical computations. That is, for example, you might somehow incorporate into your algorithm a way of inverting the matrices, let's say, much faster, or you have quantum Fourier transforms and things like that. And I put in all these things because I know things are happening, but I don't know what they are. Bioinformatics, climate change, and all this. Fluid mechanics I already mentioned to you. And I think we should welcome this change rather than saying, well, it's really only factorize number 21, which is true. That's how things begin. And pretty soon, I think they will be an important part of our research vocabulary, just the way AI and machine learning have now become and will become more and more of. So I think we have a very interesting possibility here, still in its infancy. And you can write down algorithms theoretically in certain cases, which should run fast, but there is no way to test it on the existing machines at the moment. There are really very small number of qubits, and errors are too many, and things like that. But that will be improving constantly, and so we should be looking for a future time where I would think that the scene would be somewhat different. Thank you very much. Yeah, this was my plan was to run you out on time. So this was. Thank you very much. Thank you. May I give this to Professor Maitrey? I'll come back and come back for that. So here we go. Thank you. Thank you for waiting. Okay, thank you. I have to see what it says. Okay, all right. Thank you so much. Yeah.
Thank you.
Okay, all right. Thank you so much for this opportunity.